So, now we are going to discuss the structure, properties and applications of rotor span yarns. Let us first discuss why structure is so important for any yarn. It is because the yarn property is a function of fiber properties and its structure. For any span yarn for that matter, the property of the yarn is dictated by the intrinsic property of the fibers that we are using in making the yarns, and then what comes is the structure part of the yarn. Structure basically means the arrangement of the elements, that is the fibers, their dispositions within the yarn, that is how the fibers are located within the yarn. That is all about the structure. So, you will find that different yarns have different structures, that is the arrangement of fibers within the yarn, the shape of the fibers within the yarn, they differ from each other depending upon the technology that has been used to produce the yarns. So, whenever we go from one technology to the another technology to produce the yarns, even though the fiber may still remain same, but the structure will change. That basically means the fibers and their locations, the way they are twisted, the configuration of them, they differ, and as a result the properties will change. Now, when it comes to structure, there are two aspects of it. One is the surface structure, which is actually visible to us if we look at a yarn under a microscope. Whatever we see on the surface, that is the surface structure of the yarn. That gives the texture part of the fabric as well. The other part which is not visible is the internal structure of the yarn. So, we can say structure has two components, surface structure and internal structure. The general structural features of a rotor yarn we are going to discuss now. So, we can see there is an image of a rotor yarn, that is what is shown. What we see from this image, generally the rotor span yarns are more voluminous in comparison to ring yarn. This is generally true. The surface is rough. We can see, look at the fibers on the surface. The fibers are haphazardly lying there, and they are not really well aligned. Their inclination angle of the surface fibers is not really constant. They are varying from place to place, and because of all these, the surface of the rotor yarns are very rough, whereas the surface of ring yarns are much smoother, because the fibers are well aligned there. Next thing is, loose wrapper fibers can be seen on the yarn surface. We will find lot of fibers which are loosely wrapped. They are really not twisted, they are simply wrapping around the main body of the yarn. We call them wrapper fibers. This will be also visible, and in general fibers are less parallel. What we see on the surface and what lies within, in both the cases the fibers are not really very parallel with respect to the axis of the yarn, neither with respect to the axis of the fiber themselves. Relative to each other, they are not very parallel, and with respect to the axis of the yarn also they are not parallel. See, this is another typical feature. The other part is the hairy ends. See, this is a, what you see here is a hair, this is also a hair, this is also a hair. These are hairy ends. These ends on an average are much less in the case of rotospan yarn in comparison to ring yarns. So, these are the typical some features. Now, we will go a little details of the structure. So, rotor yarn structure has two components, as we have already discussed. One is the surface part of it, the other one is the internal structure of it. In the surface part of it, what is visible to us is diameter and its variation, the surface fiber dispositions, the projecting out fiber ends. These three things is what is can be seen when you look at a yarn under a microscope. The internal structures are related to the arrangement of fibers, the migration characteristics of the fibers keeps on migrating from one radial position to another radial position within the yarn. We call it migration. The shape of the fibers, the fibers which are lying on the surface, their shape will be visible, but what is lying within the yarn, their shape is not visible to us. They remain within the yarn. We need a special technique to look at those fibers which are within the yarn structure and not visible when we take a photograph of it. The other thing which will be important is the packing of fibers within the yarn cross section, how the fibers are packed. Packing can affect many properties, and therefore, fiber packing is something which is important when we discuss about the structure of any yarn. Now, when we discuss the diameter, here we see two rotor yarn images, both are rotor yarns, and you can see the way the fibers are there on the surface. Many fibers appears to be quite loose. The diameter, when you look at it, generally the rotor yarn diameter is usually a little larger than the equivalent ring yarn diameter. And why is it so? This is because of low packing of fibers within the yarn. The packing of fibers within the yarn is relatively less in comparison to ring spun yarn. Why we are going less? We are going to discuss it. The diameter of the yarn is generally 5 to 10% greater than an equivalent ring yarn diameter. That if they use the same fiber and make the same yarn count, then generally it has been found that the rotor yarn diameters are 5 to 10% more. So, this is typical. The values could be a little more in some cases also. These are basically typical values. So, usually the rotor yarns are little fuller, therefore, in comparison to the ring yarn. Now, if we go to the surface fiber dispositions, then rotor yarns have three part structures generally. That is, they have some fibers which are known as core fibers, some fibers which are known as sheath fibers, and some fibers which are known as belts. So, the fibers which exist in the yarn, they can be classified into three groups: core fibers, sheath fibers, and belts. 15% of the fibers are wrapped around the yarn core loosely, and that is known as sheath fibers. So, the wrapper fibers, what we see there, part of them are basically sheath fibers. They are loosely wrapping around the main core of the yarn, the core part of the yarn, core part of the yarn will look little dense, and we will find, as it is seen here, that there are a lot of loosely wrapped fiber around it. These are known as sheath fibers. Then, so there are some fibers which are tightly wrapped around the yarn core, and they are usually placed at an angle of 90 degree with respect to the yarn axis. You can see some fibers which are here like this. They are placed at 90 degree with respect to the yarn axis, and we can see them that they are tightly wrapping the core as if it is a belt. So, they are known as belt fibers. So, they are also wrapping. The only difference is that they are tightly wrapping the core, while the sheath fibers are loosely wrapping the core. So, these are the two types of fibers that is visible on the surface, other than the hairs that we also see. We can sometimes see some loops also, like here is the loop, here is a loop. We can say that there are certain fibers which are forming loops. Their percentage is much less, and they basically contribute towards the hairiness part of the yarn. The projecting ends are known as hairs. That is true for the case of ring spinning also. So, we are having, as I shown the diagram, now I have shown it with these circles. These are basically hairs of the anything that is projecting out the yarn core, projecting out of the yarn core, they will be known as hairs. Even a projecting out loop also could be considered as hairs. Out of now, if we leave these fibers, the rest of the fibers are in the core part of the yarn, and they are known as core fibers. The rest of the fibers remains in the core, and therefore, they are known as core fiber. So, that is how the fibers can be classified. Core fibers. So, majority of the fibers are forming basically core. Then you have sheath fibers, which is typically around 15%, and there are some fibers which we call belts, which could be hardly 1 to 2%. So, this is how the fibers can be classified within the yarn. Now, point is how these fibers are forming. So, mechanism of formation is something which we need to know, because we will see that what role this fiber plays in deciding the properties of the yarn. And therefore, if we want to regulate or control the property of a yarn, then we have to regulate or control the formation of these fibers. And for that, we need to understand what is the mechanism of formations of sheath fibers especially, and belt fibers. Now, we all know that fibers, after they get separated, we feed a sliver, open it out or separate them with the help of opening rollers, and then these separated fibers are made to enter the rotor spinning chamber. Now, when they enter the rotor spinning chamber, the entry point is fixed in space, but the rotor chamber keeps on rotating at a very high speed. So, the fiber can land anywhere within the rotor. The total periphery of the rotor is around 2 pi r, where r is the radius of the rotor. So, the fiber can land anywhere within the rotor groove. Those who land completely outside the PTE zone, as shown it here. So, PTE zone is shown in here. PQ, if we write it, then this is the point P and this is the point Q. See, this is what we are showing it here in the left hand side is a circle is representing the rotor, the groove part of it, and this is what we have seen earlier. This is the yarn arm, which keeps on rotating as the rotor rotates, and then here is the yarn which is taken out in these directions, and part of the band of fibers within the rotor groove is twisted, and that is called partially twisted, and we call it PTE, peripheral twist extent, or sometimes in some books you may find it is written as twist transition zone. So, from P to Q is the twist transition zone, because beyond the point Q the fibers are practically parallelly laid within the groove. So, the twist reaches up to the point Q, and the Q actually is, let us say, point on the rotor groove. So, part of the fiber band which is lying within the rotor groove is twisted, and we call this zone as PTE zone, peripheral twist extent zone. So, anything that when the fibers are falling anywhere outside this PTE zone, like this blue fiber, then or if another fiber could be somewhere here, another fiber could be here, all these fibers are outside the PTE zone. So, if they happen to land in an area beyond this PTE zone, and also the zone dictated by this one, that is the critical fiber deposition zone. That is, if I say P Q is the PTE zone, then on this other side also there is little, we can extend it on the left hand side also, and if I give a name to this particular point, let us say I give it a name R, then from Q to R is an area within the rotor groove which is known as critical fiber deposition zone. That is, if the fiber lie within this zone, then there is some possibility that the fiber will be part of the sheath fibers. However, if they lie beyond this PTE zone and also the zone PR, they become part of the yarn core, then they become part of the yarn core. So, if the fiber happens to lie anywhere beyond the RQ zone, then they will be part of core of the yarn. And we will see now that what happens if the fiber land in the PQ zone or in the PR zone. We call this critical fiber deposition zone, because if they land here, what happens to these fibers? We are going to discuss this point now. In this diagram, these are the fibers which are outside the critical fiber deposition zone. So, all these fibers is going to be part of the yarn core. Now, what happens that when the fibers are entering the rotor chamber, then within the rotor the yarn arm is also rotating at a very high speed. So, rotor is rotating, the yarn arm is also rotating. So, it may so happen that some fibers while entering the rotor chamber fall directly on the yarn arm. So, this is the fiber which is shown here, and they may directly land on it. It may happen for some fibers, and if it so happens the yarn arm is already twisted. So, therefore, anything if a fiber is landing on it due to whatever reason, because the air within the rotor is also a kind of vortex, and therefore, some fibers may finally find to land on the yarn arm. The yarn arm is rotating with respect to the yarn axis also, and also rotating with respect to the rotor axis. Now, if a fiber lands on it, the fiber end will be caught by the yarn arm, and if it is caught, then the fiber will be wrapped around it, because the yarn itself is rotating on its own axis. The once these fibers as shown it here in the orange diagram, the orange color fiber which has landed on the yarn arm, this will be going to be picked up by some hairs or some loops which are there in the yarn arm, and once it is caught, it will immediately be wrapped around the yarn core, the twisted part of the yarn. It cannot penetrate and go inside, because yarn has already formed. So, it has to then stay on the surface, and it will stay on the surface in the form of sheath fibers. That is what is going to happen for those fibers which are going to land on the yarn arm. Now, we are discussing about some fibers which are landing in such a way that part of it is in the PTE zone and part of it is lying where untwisted fiber band is lying in the rotor groove, like we are showing it here by the orange colored fiber. So, if you orange colored fiber, see from P to Q is our PTE zone, the fiber is represented by DEF. So, the DE part of the fiber is within the PTE zone PQ, and EF part of the fiber is outside the PTE zone, and it is basically has become a part of these fibers which are lying parallelly in an untwisted state within the rotor groove. Now, what is going to be the fate of this fiber? Part of it is in the rotor groove where fibers are untwisted. So, this part is going to form the core part of the yarn. Rest of the fiber, that is the D part, will be partially wrapped on the yarn core, and it will form a sheath fibers. That means, the same fiber, what we will see, part of it is forming the core and the rest of it is forming the sheath. So, we will have many fibers like this, where some part of it is forming the core and some part of it is forming the sheath fibers or wrapper fibers. And the proportion of such fibers will depend upon the ratio S by pi dr, where S is the length of the PTE zone. So, this PTE zone from here to there, that is PQ, PQ is basically in terms of length, it is S. So, this proportion of these fibers will depend on the ratio of S by pi dr, where S is the length of PTE and dr is the rotor diameter, that is rotor circumference is pi dr and S is the length of PTE. For the given fiber, this is going to depend upon this S by pi dr. So, this is there could be many fibers like DEF, whose part of it maybe few millimeters will be within the PTE zone and the rest will be a part of untwisted bundle of fibers. So, this many fibers will be able to see which will belong to this category. And then comes another type of fibers, where you see here in this diagram that is D if this fiber has landed in such a way that part of it again is in front of P, therefore, it will form the wrapper fibers or sheath fibers. Let us say in this case the EF part of the fiber is going to form sheath fiber, because EF part is all landing on the peripheral twist extent zone, what fibers are already twisted to some extent. Now, this fiber, this part of the fiber will receive little bit of twist and it will basically a kind of wrapping will be there. The other part, D part, will be how it will look like. Now, as the fibers, since the yarn is being withdrawn, so what will happen? The fibers will get filled, that is, this fiber will change its position from here to there, it will be like this. Further, it will be like this, and so what will happen? As the yarn is being withdrawn in these directions, this fiber DF will be pulled along with the yarn and it will be folded. So, it will have two parts now. One part is basically partially staying in the PT zone, the other part is actually on the already formed yarn, that is on the yarn arm, and therefore, what is going to be the configuration of this fiber now? This fiber will be folded and then wrapped. That is going to happen to these fibers, and proportion of such fibers will depend upon the ratio of L by pi dr, where L is the fiber length and dr we have already said. So, in case the fibers lie or land the way it has been shown here, then this is going to be the fate of the fiber. So, it is going to be some kind of wrappers is going to be formed, and this is the way in which fibers are forming. Wrapper fibers, we call them sheath fibers also, and some of them will be tightly wrapped and we call them belts. So, we will find many fibers like this. That could be some fibers which are partially forming, part of it is forming the sheath fiber and part of it is actually within the yarn core. So, it is buried in the core, one part, the other part is lying on the surface. So, one end or one part is a part of the core and the other part is part of the sheath. This kind of fibers also will be visible. The wrapping fibers or these sheath fibers, it has been shown that for constant fiber length or constant fiber length array is shown it here, the proportion of such fiber is going to be L by 2 divided by pi dr into 100 L by 2, because 50% of the fiber length form wrapping around the twisted core. That is why this value is coming L by 2, whereas for triangular staple length which is close to cotton, this value is going to be half L max by 2 into 50 by pi into dr. So, when the fiber length is constant, this is L. When the fiber length is not constant and following a triangular array, then we can L we replace it by L max by this 2. That will give you the proportion of wrapper fibers that we can roughly expect in the yarn. Now, the next topic of discussion is twist. See, rotor yarns do not have a constant twist across its cross section. This is something quite different from ring yarns. Rotor yarns do not have the constant twist. It has a differential twist structure, that is, twist varies across the yarn cross section. So, twist is not same throughout the cross section of the yarn. The twist is more in the core and less on the surface. So, core part of the yarn receives more twist, whereas surface part of the yarn, sheath fibers, they actually slip while they are getting wrapped. There is a chance of slippage, and therefore, there is a loss of twist in the sheath fibers. As a result, the twist distribution is not uniform from core to the surface of the yarn. Exact twist measurement therefore becomes difficult following untwisting twisting principle, because by the time, see, the surface fibers are inclined at a certain angle which is less than the core fibers. And if it is so, if we try to untwist the yarn in order to estimate or measure the value of twist in the yarn, and what will happen? By the time we will untwist the surface fibers and make them parallel, the core fibers are still having some twist. So, what we will find that in such condition, if we try to stretch the yarn is not going to break. This will not going to happen in the case of ring yarn. In the case of ring yarn, if we remove twist by untwisting, and if we, when we make the fibers surface fiber parallel with respect to the yarn axis, then if I stretch the yarn will break, and it will break because of slippage of fibers, because there is no twist left in the yarn, and the simply little bit of stretch, the yarn will break because fibers are going to slip. This is not going to happen in the case of rotor yarn. By the time you have made the surface fiber parallel by untwisting on a twist tester, the core fibers are still having twist, and hence if I stretch it, the yarn is not going to break easily. There is no slippage. Now, what we should do? People may try to further untwist it. So, they keep on untwisting in order to make the core fibers parallel, so that they lose all twist and becomes parallel to each other. What we will find that the surface fibers are now getting twisted in the opposite directions. So, by the time we make the core fibers parallel, we will find the surface fibers are twisted now in the other directions, and so surface fibers will be tightly wrapped now, and they will hold the core fibers together. Even though core fibers are parallel, if we try to stretch the yarn is not going to break easily. Therefore, twist determination in the case of rotor yarn is something which is difficult, and we cannot measure the twist accurately. This will not be the case in the case of ring spun yarn. So, measured twist based on the tension sensing principle shows 5 to 30% less than the machine set twist. So, whatever twist is set on the machines, if we try to measure the twist based on tension sensing principle, we will find that the twist value is less by 5 to 30% in the yarn. This is with respect to whatever twist we set on the machine, is the mechanical twist or machine twist that we set. This is what is the. Now, in this diagram, we are trying to show the yarn cross section, how the twist is going to vary across the cross section of the yarn. So, this is the yarn cross section, and the cross section has been divided into 3 zones, zone 1, zone 2 and zone 3, and the twist variation is shown. So, what we see here at the core, this is the level of twist. This twist goes like this, and in the zone 2 the twist is declining. So, in zone 1, that is the core part of the yarn, the twist is practically constant. And so, in zone 1, found fiber deposited outside the PT zone, and here the twist is practically constant over the yarn cross section, and the percentage of fibers in total quantity of fiber assuming constant fiber length is going to be around 75 to 90%. This is A1 is how much? Is 1 minus, this is the approximate equation to find out the percentage of fibers which will belong to A1 category, that is the core fibers category. Now, why this has come? We will come to know gradually why it is 0.5 LF plus S. So, the core part from here to there, that is zone 1, the twist is practically constant. Then comes zone 2, the twist is actually declining. So, this declining point is zone 2. So, from fibers deposited in the PT zone. So, these are basically because of the fiber deposited in the PT zone, where the fibers are partially twisted, and therefore, when a fiber lands on this area, it will also be receiving not the full twist, but little bit of twist, and this twist will gradually be less and less, depending upon how much part of the fiber is lying on what part of the PT zone. On the PT zone itself, the twist is 0 to the maximum level of twist that we get in the yarn, because twist is not constant in the PT zone. In the PT zone, see, it will be like this. These are the suppose straight fibers, parallel fibers, then here the fibers are a little bit of twisted. So, twist is initially less, and then you have parallel from here to there, let us say is my PT zone, and then onwards this twist is full as the nominal yarn twist. So, here when the fiber is lying here like this, part of it is receiving some twist and part of it is receiving much less twist. So, here this zone, this will receive more twist, this part will receive less twist. So, like that, on an average it has been found that the fibers which are in this area, they are basically almost part of it is forming sheath. Twist level is declining in those fibers which are in zone 2, and their number is basically 3 to 10%, and this gives you an estimation of the A2 type of fibers which are in zone 2, S by pi dr into 100, where S is the length of the PT zone. So, this is my S. And then comes twist distribution again, but now zone 3, this is the zone we are discussing now. What we see here? These are formed by the fibers which project from PT zone over the peel off point. A part of outer sheath layer and wrapped around the yarn core. Twist varies greatly from inside to the outside. See here, in this zone the twist which was going down suddenly changes, goes very high. So, in the periphery or the yarn surface we will find some fibers which are giving this kind of twist. Some of the fibers also we can see them twisted in, suppose we are putting Z twist, we will find some fibers with having little bit of S twist and some are also having Z twist, or the same fiber, part of it is S, part of it is Z in terms of directions. And fibers in total quantity for assuming constant fiber length in this category is going to be 0.5 LF by pi dr, and this is typically 7 to 15% depending upon the rotor diameter and fiber length. Belts will be a part of this category fibers. So, twist direction opposite to the yarn twist, like from here to there, twist direction has changed from, see, this side is Z and this side is S, this is Z, this is S. So, part of it we will see that it is having S twist followed by some fibers having, or same fibers part of it forming Z, forming S, this kind of also can be seen. So, the surface fibers what we see has a different types of twist. Core fiber mostly twist is constant, then there is a transition zone where twist is declining towards the surface, because we have said that many surface fibers or sheath fibers will lose twist because they are slipping when they are trying to be twisted. Their ends are free, the ends can rotate, and therefore, the twist leakage is possible for many fibers. Because of twist leakage, some of these fibers may not be having the full twist that the machine is going to impart on them. That is, these are the fibers which are in zone 2. Then comes the zone 3, where there are many of these are basically forming belts. They are tightly wrapped. So, therefore, the twist level you see is going very high up to this much, because they are forming almost perpendicularly placed with respect to the yarn axis. This is going to happen for some fibers. So, they may show part of it S twist, part of it Z twist also, because there is a lot of turbulence within the within the rotor, and so many fibers we are injecting per unit time. So, some of these fibers will be directly landing on the yarn arm, and they may get twisted very tightly. So, these are the, so you can say roughly that the twist across the cross section of the rotor yarn is not uniform, that is, twist in the core part is quite uniform and the core looks like a ring yarn, whereas the sheath part the twist is generally on an average less than the core part. Now comes fiber shape. A table is shown here which gives an idea about the shape of fiber, that is leading hook fiber, trailing hook fiber, central deformations and straight fibers. These are the 4 different categories, and a comparison has been made between ring and rotor, and what we see here in rotor yarn most of the fibers are deformed. Deformed basically means you will find the fibers having a shape like this, or some fibers, all kinds of varieties of shape will be visible. If we go by the tracer fiber technique, by which we can really visualize a fiber within the yarn, then you will find like this. There are varieties of shapes, though they are twisted, they are not really flat, they are following a helical path at the same time, but they are folded, they are buckled, their ends may be hooked. This is what is going to happen. All types of deformed shapes are present. Straight fibers are only about 30% in rotor yarn. The rest of the fibers are not straight. So, if 70% of the fibers are not straight, then obviously this is going to affect the many properties of the yarn. In contrast, the ring yarn will find 74% and even maybe more % are perfectly straight and parallel. Thus, we can say that ring yarns will be always stronger than rotor yarn, because most of the fibers are straight and parallel, and therefore, they participate fully in sharing the load when we try to stretch a yarn. Whereas, fibers in the case of rotor spun yarns are all basically crumbled, many of them deformed, and they behave like short fibers. Though their length is more if we straighten them out, but because their effective length goes down, they behave like short fibers, and therefore, the strength is less. That is one of the reason. Now comes another important aspect is fiber extent coefficient. Fiber extent is measured by measuring end to end distance of fiber as they lie within the yarn, like this fiber is shown on the right hand side. So, end to end distance is from here to there, this distance is the fiber extent. So, we can find out what is the average fiber extent if we look at 100 fibers, each fiber will have one value. So, average value is Fe bar is going to be sigma Fei by n, and then you can find out fiber extent coefficient, which is the ratio of these two, Fe bar by average length of fiber L bar. That will, this ratio will give us some idea what percentage of the fiber length is actually utilized or in the yarn. So, typical fiber extent coefficient for rotor yarn is only 0.49, for ring yarn it is 0.67. So, on an average we can say therefore, in the rotor yarn most of the fiber length is utilized, whereas rotor yarn it is not, because fibers are crumbled, fibers are deformed, they are having hooked. Then migration is another important phenomena. See, in all spun yarn, unless the fiber migrate, there will not be any strength in the yarn. Twisting is the mechanism or a process by which we induce migration in the fibers. And what this migration means? Fiber migration means that the fibers are moving from one radius to another radius of the yarn. Fibers are continuously made to move from surface to the core part of the yarn and core to surface part of the yarn in the case of ring yarn. And this movement of the fiber within the yarn body is actually helping to hold the fibers together. If it is not, then there will not be any interlocking between the fibers existing in different concentric zones of the yarn. So, therefore, migration is very important, that is, a fiber will move like this . This is what is known as migration. So, it is going from, this is the yarn, let us say there is the yarn. So, they are going from the surface of the yarn to the core part of the yarn and then again going to the surface, and this is they are repeating. This is what is called migration. This migration is important because without this there will be no strength in the yarn, the fibers will simply slip. If I only have fibers like this, suppose same they are that is they are following a spiral path, but there is no change in the radial position of the fiber. And there is another fiber which is also following a spiral path like this. This is following, there also there is no radial position. So, if there is a one helical path of larger diameter, another helical path of smaller diameter, there is no interaction between them. And if the fibers do not interact by moving from one radius to another radius, in that case if I pull this, fibers will slip easily and there will be no strength in the yarn. What we need is something like this, and this is what is simple term, this is what is migration. And we study migrations of ring spun yarn, rotor spun yarns and many other yarns, because it is the migration that actually holds the fibers together, and we call it an interlock structure of yarn for spun yarn. For filament yarn we do not need migrations, fibers will migrate there also if we put twist, but we do not need migration in order to hold the fibers together, so that strength can be imparted. Anyway, so migration, this particular movement of fibers within the yarn is characterized by amplitude of migrations, by mean fiber positions and by migration intensity. There is a three different parameters. I am not going to discuss in details what are these parameters, but these are the three parameters by which we characterize this migratory path that the fibers follow. Mean fiber position, if we look at first, rotor yarn 0.44, ring yarn 0.54. Low mean fiber position indicates fibers are mostly near the core part of the yarn in the case of rotor yarn. Most of the fibers or most of the length of the fiber is placed near the yarn core. That is why its mean fiber position is less. The amplitude of migration, how much they are migrating from this path to this path. See, here it is going from here to here, then going back like this. So, this is the rate of the migratory path moving, rate of movement of the migratory path towards the yarn core is called the from there we can calculate what is migration intensity, the rate. The other part is amplitude of migration, which is measured by root mean square deviation. If it is migration, what is the amplitude of this wavy path that the fibers are following? Now, this is what it is shown here, rotor yarn 0.24, ring yarn 0.32. That is, the amplitude of migrations is less in the case of rotor yarn in comparison to ring yarn. What does it mean? That basically means that migration is more local in the case of rotor spun yarns. That is, they are not cutting across the cross section part of the yarn is little bit less in the case of rotor yarn. That what basically means, that migration is more localized it is not happening across the full cross section of the yarn, whereas for ring yarn it is still better, this value is more. And the intensity, as I said, the rate of change of the migratory path as it moves from surface to core, core to surface, that intensity is more for rotor yarn, less for ring yarn. That basically means that the rate of change of radial position is higher in the case of rotor yarn due to more twist used to spin the yarns. That is the reason. Generally, we use more twist to spin rotor yarn, because we expect some fibers to lose twist. See, point is, as the fibers are twisted, the fibers are pressed against the rotor wall due to centrifugal force. There is no other mechanical device to hold the fibers together. Like in the case of ring spinning, when the fibers are twisted in the delta zone, the trailing end of the fibers is they are under the nip, they are gripped firmly by the pair of front rollers. That grip is very, very firm. So, if we twist the other end, the front end of the fibers, the trailing end of the fibers cannot rotate and lose twist. This is something which is not there in the case of rotor spinning, because the fibers are simply pressed by centrifugal force. There is no pair of rollers to hold the fiber ends. So, therefore, when the front end of the fibers get twisted as the torque flows, the trailing end may rotate a bit on its axis and therefore, can lose some twist. So, twist loss is possible in the case of rotor yarn, and to compensate that we use generally a higher level of TM, twist multiplier in rotor yarn in comparison to ring yarns. So, this excess twist multiplier that you use can also lead to a very high migration intensity. That is the reason why migration intensity could be higher. So, these are all typical values. So, the exact values for a given type of fiber or kind of speed at which the yarns have been spun, the values may little bit differ from each other. The next one is hairiness. Overall hairiness is lower in rotor yarn in comparison to ring yarn. First of all, the hairiness is little less, though percentage number of short ends are larger in rotor yarns, the percentage of long projecting ends are lower. So, long projecting hairs are much less in the case of rotor spun yarn. Many fiber ends remain suppressed under the belts. The belts are tightly wrapping. So, therefore, some fiber ends actually remain suppressed and they cannot project out, and therefore, also we can say the hairiness becomes less in comparison to ring yarn. Then comes packing coefficient. Fibers in rotor yarns are less packed than ring yarn. That reflection also we get in the mean fiber positions. That packing is coefficient varies between 0.35 to 0.55. On the ring yarn, it will be close to 0.5 and can go up to 0.65, 0.6 depending upon the level of twist. Lower packing is due to deformed shape of fibers within the yarn and low spinning tension. Tension under which the yarn is spun, that is tension at the yarn formation point, is less in comparison to the tension that the fibers experiences in the delta zone of ring spinning. Packing is also not uniform across the cross section of the yarn. So, the packing is maximum at a distance of 1/3 to 1/4 of the yarn radius from the yarn center. So, packing is not constant. Packing is also not constant for ring yarn as well across the cross section of the yarn. So, fibers are packed more near the center and packed less on the surface. That is true for ring yarn also, and this is also true for rotor yarn as well. Surface fibers are a little less packed, core fibers are tightly packed. That is how the packing coefficient varies from surface to core. And this low packing is because of the buckling of fibers and possibly wrapped ribbon form of transformation of fibers into yarn. So, twisting phenomena or twisting process has been described by Hurl that it could be wrapped ribbon type of twisting depending upon the spinning tension under which the bundle of fibers, a ribbon of fibers is actually twisted. In the case of ring spinning, a flat ribbon is twisted, but in the case of rotor yarn, it is not really a flat ribbon. It may be a triangular shape it takes within the rotor groove, the bundle of fibers, and then that is twisted. So, there is a chance that the buckling phenomena could be there because many fibers are actually buckled and deformed. The other thing is the wrapped ribbon form of twisting also may be possible when the bundle of fibers are transformed from a bundle to a yarn, a twisted yarn. Now, to discuss about property. So, the structure part is now we have completed, we will move to property. As I said, it is the property of the fiber and the structure. These two actually decide the property of the final yarn, and similarly the yarn property and the fabric structure will decide the property of the fabric. So, property, first of all, strength. Breaking strength is always lower with respect to ring yarn. We are always comparing with respect to ring, because ring is the yardstick. We want to judge the quality of other yarns spun on other technologies with respect to always ring yarn. Breaking strength is lower. Why? Presence of deformed fibers, poor fiber orientation, non-contributing wrapper fibers. Some fibers are loose, some fibers are tightly packed in the core. So, when you stretch the yarn, the core fibers will take the load, the wrapper fibers are not going to share the load. So, automatically the strength will go down. Besides, the fibers are deformed also and the migration is also less. All these are the reasons. CV of strength is better, however, because the yarns is more uniform. Why it is uniform? Because of more number of doublings, back doublings, if you remember that word, that happens within the rotor, and directly we are feeding fiber. So, there is no chance of generation of drafting wave by the rollers, which we get in the case of roving frame and ring spinning machine itself. This is something which is missing, and hence the uniformity is better. Breaking elongation generally higher. Why? Because of deformed and disoriented fibers. So, when you stretch, these fibers try to unbend first, and hence the breaking elongation of these yarns are generally more, but maybe less for long fibers also. This also has been seen, and the fibers are too long, then breaking elongation of the rotor spun yarn may be little less than the equivalent ring spun yarn. Stiffer, the bending rigidity is more. Why? Because of tightly formed wraps by the belts. The belts actually is tightly holding the fibers, the core fibers, and therefore, when you try to bend it, the core fibers cannot really move. See, whenever there is a bending of a bundle of fibers, what happens that some fibers are trying to move with respect to the other fibers. If the cross section of, suppose I want to bend a yarn, suppose this is my yarn, and we all know the beam bending neutral axis, this, let us say these are the fibers, and what happens that these fibers on the surface of the cross sections, and this is the cross section of the yarn, they will try to stretch, whereas the fibers which are below this neutral axis here, these fibers are going to get compressed. So, they are going to stretch longitudinally, they are getting compressed longitudinally also, that is, and as a result there is going to be a lot of shear between the two group of fibers, and if the shear possibility is allowed, that is, if we allow the fibers to slip over each other while their whole structure as a whole is going to bend, then the bending rigidity will be low. But if we make tight bands over here, and tight bands mean lot of force which is acting radially, in that case what will happen? The fibers relative movement between the two group of fibers will be restricted, and we need more force now. So, bending rigidity is going to be high. Therefore, presence of tight belts is the reason why the rotor spun yarns are stiffer in bending. Uniformity already discussed, that is, physically they are better uniformity because of high back dabbling and random arrangement of fibers. Imperfection is generally lower because of back dabbling within the rotor evens out the mass variation. Therefore, thick thin places are also much less, but sometimes you have to remember that the wrapper fibers sometimes get counted as naps. Wrapper fibers, the loose wrappers can slide and they accumulate and form naps. The other thing is the belts increase the mass locally and they can be counted as naps also. So, sometimes the naps number may go high, even though if we look at the yarn we may not be able to find too many naps. Volume is always greater because of low packing density, which is because of lot of deformed fibers which are there. Surface is generally rougher, we have seen the surface of the yarn, lot of disorientation is there, belts are there, and as a result the yarn is not smooth, it is quite rough. Hairiness is lower, that also we have seen because of the wrapper fibers cover the projected fiber ends. The belts are also suppressing lot of hairs, not allowing them to project out. Property resistance to abrasion is better because the belts which may slide on the yarn due to abrasive stress, and wrapper fibers also can do the same thing, sometimes they accumulate and they keep sliding and they reduce the abrasive stress on the core part of the yarn. Handle is harsher because the bending rigidity is high. Luster is duller because the surface fibers are highly disoriented. This is in comparison to the ring yarn. knot strength is lower because the yarn strength itself is low because of reasons already stated. And how does it influence the yarn property? Covering power will be better because the yarns are fuller and bulkier. Resistance abrasion is better because the wrapper fibers can slide and absorb the abrasive stress in the fabric also. Air permeability higher as the yarn is more porous because of low packing. Shrinkage lower as fibers remain under lesser axial tension level when twisted into the yarn. If we take the yarn and dip it into water, we will know that the yarn shrinks. Now, this shrinkage depends upon the spinning tension under which the yarn was spun. In the ring yarn, the spinning tensions are always higher. There is a big balloon, there is a traveller, and the entire balloon and traveller has to rotate, and there is a friction on the ring and traveller. So, as a result, the spinning tensions are very high. So, fiber in the delta zone experience more tension in comparison to the fibers in the twisting zone or the yarn formation zone of the rotor spinning process. And because they undergo lesser axial tension during transformation from bundle of fibers to twisted yarn, their shrinkage is less. Peel formation tendency is also lower as hairiness is less due to wrapper fibers and belts. So, peeling tendency is less. Luster is dull, the fabric luster will be dull because the fiber surface is having loss of disoriented fibers. So, the yarn is dull, the fabric also will be dull. And now we go to the end use, that why the rotor yarns are generally used. So, once we know the property, the typical end uses are blankets. Rotor yarns are generally, we produce coarse yarns. Generally, the count value of the yarn may vary between 6 NE to 20 NE. This is the range in which we spin the yarn. So, generally in the coarser category of yarn counts can be produced, and so any product that needs coarse counts, rotor yarns can find a place there. So, blankets is one place, denim is another, where these rotor yarns are very much used, though ring yarns are also used for denim, but rotor yarns can also be used because we can spin the yarn at a coarse yarns, and denim needs coarse yarn because we want to produce high GSM fabrics, we need coarser yarns. So, yarns are bulkier, and the other thing is that commercially they are cheaper, therefore, they are very suitable for this. Also, we can go for fleece fabrics, home furnishing products, terry towel also people have tried, though it become little harsher if you try to form the piles, but in the ground they can be easily used. So, they are finding place in the terry towel also, and they can also be used as industrial yarn. Now, with this we conclude this particular discussion on the structure and properties and end use of rotor yarn. So, with this the rotor yarn is now, or rotor spinning is now finished. In the next lecture we will discuss some other spinning system. Thank you.